Okay, so now we're going to touch base on derivatives, or start to calculate derivatives. But before we even do that, we're going to look at rates of change. So you are used to seeing rates of change in the terms of m as the slope is equal to the change in y over the change in x. What you've been calculating before is also called the secant slope, and it usually occurs over an interval. So m secant is generally calculated as f of b minus f of a, so your y values, all over your x values subtracted. So that's your m secant. Now we're going to apply this and finding the rate of change over this f of x and using this interval. So first we need to find our y values. We're given the x here because that's our interval, and we're going to plug it into our f. So we need to find f of 1 and f of 3. So f of 1 is 1 cubed minus 1. F of 3 is 3 cubed minus 3. So for f of 1, we're going to get 0. And then for f of 3, we're going to get 24. Now I'm going to plug it into my slope equation. This is going to be 24 minus 0 over 3 minus 1, which is 24 over 2, and then our slope, our m secant, is going to be 12 in this case. Now that's how we're going to find an average rate of change over an interval. The instantaneous rate of change occurs only at one point, and it requires calculus to help us find this instantaneous rate of change. So I'm just going to draw a picture to begin with so we can actually visualize what's going on here and the difference between the two. So let's just say we have 2 points, A and B. This is going to be your f of A. Here is going to be your f of B. So that kind of lines up with those 2 points. What we calculated before is really the slope between those 2 points. And that would be your secant. Now for your tangent, this occurs at one point. Let it be the B. So if you look at the slope right over here, it looks like it's going down. It's a downward slope. So you would, for your m secant, it's going to be your slope between 2 points, but the m tangent is going to be the slope at that exact point at B here. This would be your tangent then. So this is your tangent, and this will be your secant. So for our m secant, we know how to calculate that. We have it up here. But we don't really know how to find m tangent yet. In question 3, example 3, we're going to try to find m tangent using m secant, but it's just going to be approximate. It's not going to be the exact thing, and you're going to see why. So for example 2, we're going to find the equation of a secant line for our function on an interval. First thing you're going to do is find the slope, so your m secant. And when you find the m secant, we're going to need our y values over this interval. So that means for 0, I'm going to have e to the 2 times 0, which is e to the 0, and that's 1. And then I have e to the 2 times 2, which is e to the 4. So for my m secant, we're going to have e to the 4 minus 1 over 2 minus 0, which is e to the 4 minus 1 over 2. We're just going to leave it like this because we don't have a calculator. And then afterwards, I'm going to put into the equation. So the standard equation we're going to use is of this format. Y squared minus y1 is equal to m times x squared minus x1. And then from here, we're going to pick a point. That's kind of given to us in our interval. So we could pick either 0, 1, or we could have picked 2 e to the 4. So that's their points from our endpoints here. So I'm going to pick one of the two. Either one doesn't matter. And we're going to replace m with the slope that we found. So y2 we're going to leave alone just as our variable. So y minus, let's just pick this one. So that'll be 1 for our y value is equal to our slope, which is e to the 4 minus 1 over 2. We're going to leave our x2 as just a variable, and then our x1 is going to be 0. So that's going to be the equation of our secant line, and we can just leave it as that. You can also simplify it, but it's not necessary. So for example 3, we want to estimate the slope of the tangent line. As I was saying before, we can use the symmetric difference quotient. But to use our secant formula for the symmetric difference quotient, we need it to be on an interval. So we're just given a point here, but let's create an interval that fits this. So we're going to get close and closer to 1, as close as we can. So let's just use, for example, 0.9 and 1.1 as our interval for calculating this. So what we're going to use is called the symmetric difference quotient. And this will give us approximately what m tan would be. So this would be our y value when we plug in 1.1 minus our y value when we plug in 0.9 all over 1.1 minus 0.9. So this is going to be e to the 2 times 1.1 minus e to the 2 times 0.9 all over 1.1 minus 0.9. So you can plug this into the calculator. You're going to need to for this one because there will be a lot of decimals. This is going to be about 14.877. Now, if you want to be more accurate with what we're using now, we can just pick a different interval, but just be even closer to 1. So I'll just do one more extra example with you here. We could have used y of 1.01, which is even closer than 1.1. And then we could have used 0.99, which is even closer to 1. And if you have done this calculation, we would have gotten 14.778. And if you want to get even closer, then you're going to add more decimal places, and eventually this would converge to a certain number of 14.7 something. Here's some application of the secant and tangent lines. So if you've taken physics, average velocity and instantaneous velocity will look very familiar to you. So if you think about average velocity, this is calculated as d final minus d initial, which is your displacement, over t final minus t initial, which is your time. So if you think of your symmetric difference quotient, which is your m formula, they look kind of similar to each other, but they just have different variables. Okay, so we're going to apply this to finding the average velocity. And then your tangent, m tangent, is the same thing as saying your instantaneous velocity. Sorry, it's missing an L over here. So that's the same thing as finding instantaneous velocity. And again, the only thing that we can do right now is get as close to as possible by finding an interval to use our slope formula. Okay, so in a time of t seconds, a particle moves a distance s meters from a starting position where s is equal to 3t squared. We want to find the average velocity between t and t equals 1 plus h if h is 0.1. So for our first one, to find s, which is our distance, is going to be s of 1.1 minus s of 1. Okay, so t is equal to 1, and then 1 plus 0.1 is 1.1. It's going to be over 1.1 minus 1. And now I'm going to plug it into my s, which is 3t squared. So that's 3 times 1.1 squared minus 3 times 1 squared all over 1.1 minus 1. If you do that calculation, it's going to be about 6.3 meters per second. Now we're going to do it for the next one. So now our value is going to be 1 and 1.01. So let's see, S of 1.01 minus S of 1 over 1.01 minus 1. So if you plug this in your calculator, do the calculations, this would be 6.03 meters per second. And then lastly, we have 1 and 1.001. And this is going to be, if you do the calculations, 6.003 meters per second. So if you look at all of our answers in A, we got closer and closer and closer to t equals 1 by having a smaller and smaller interval. Now, if you look at how our numbers changed, it went from 6.3 meters per second to 6.03 to 6.003. So really, once we get closer and closer to 1, it's probably going to converge until 6 meters per second. So we can say that m tan at t equals 1 is going to be about 6 meters per second. And that's it for our lesson. So please check your homework section to see if there's any worksheets there. I think I posted one that you could try already.